In this video, we'll address the issue of repeated eigenvalues for trying to solve constant coefficient system differential equations. So repeated eigenvalues, if you look at things randomly, don't happen all that often, but they can happen, and they also help illustrate what happens as eigenvalues get closer and closer together for solving systems in general. Let's look at this system here. 6, 8, 2, minus 2. Let's try to find the eigenvalues, eigenvectors of this system. So for this matrix, we have that A minus lambda I is the matrix 6 minus lambda minus 8, 2 minus lambda. We can then find that determinant, and I get 6 minus lambda minus 2 minus lambda plus 16. This I will get a lambda squared minus 4 lambda minus 12 plus 16, lambda squared minus 4 lambda plus 4, and that factors as lambda minus 2 squared. Here we have a double eigenvalue at 2. Now if I look for eigenvectors for this, a minus 2i is 4 minus 8, 2 minus 4, which those are redundant equations, and it becomes 1 minus 2, 0, 0 after row reduction. So my eigenvector could be 2, 1. That works for making this go to 0. So I have a double eigenvalue. It has power 2 here, but I only found one eigenvector. And that here is the issue. The issue being we have what's called a defective eigenvalue. This means that the power in the characteristic polynomial is strictly greater than the number of linearly independent eigenvectors. Or if I want to be fancy, that last part is the dimension of the set of all eigenvectors of a certain eigenvalue, or the eigenspace of that eigenvalue. But this is a problem, because if I want to get to n linearly independent solutions, or in this case 2 solutions, I don't have enough eigenvectors and eigenvalues to make it happen. I need n different eigenvalues and with corresponding independent eigenvectors to make it happen. With the example on the previous page, we know then that we have one solution of the form 2, 1, e to the 2t. That will solve the problem, but I don't have a second one. I don't have another eigenvalue to pull from. I can't find a different eigenvector. Nothing else sort of we have so far that'll give us towards a solution. So we need to find another solution somehow to be able to then get to a general solution for this problem. But again, we already have a trick up our sleeve for trying to do this. So we dealt with this issue before, and that was with repeated roots for second order equations. What was the result there? We did reduction of order, which led us to multiplying by t. So let's try that here. We had our system where this matrix here was 6 minus 8, 2 minus 2. And now let's try guessing t times e to the 2t. So we're going to guess a solution of the form v for some vector v that we don't know. This is our unknown constant before, times t e to the 2t. So if I do that, then the derivative is going to be v times e to the 2t plus 2v t e to the 2t by the product rule. And I want this to equal a times that, so a v t e to the 2t. And see, there's a problem here. The problem here is that on this side I have this e to the 2t term that's not over here, which means v has to be 0. That's bad. So that wasn't a good enough guess this time. It worked for the constant coefficient second order case, but it doesn't work here. So what can I do instead? Well, if I add in an e to the 2t term, maybe I can get rid of this v term. So new guess, we're going to guess x to be v t e to the 2t plus another vector w times e to the 2t. And now let's see what happens here. If I differentiate this, I will get 3 terms this time. I'll get the same v e to the 2t. I will get the 2v t e to the 2t. And I will get a 2w e to the 2t. And I want this now to equal a times x, or a v t e to the 2t, plus a w times e to the 2t. And now let's group these two by the function of t that's attached to the end. So for just e to the 2t, what I see on here is v plus 2w equals aw. And what I see for t to the 2t is 2v t to the 2t equals av. So what do we see here? Well, this I recognize. This is an eigenvalue equation. And if I move this over here, I get something that looks kind of similar. So from the t to the 2t, we see that we want to solve av minus 2v equals 0. That is, v is an eigenvector of a with eigenvalue 2. But we did this already. We know this 2, 1 vector works for this situation because that was the eigenvector we found in the first place. Now, from e to the 2t, we get that we want aw minus 2w equaling v. This is almost an eigenvalue equation, except I don't have 0 on the right. I have v, where v is this eigenvector from the first part. So now I have to go back and solve my equation here again. So aw minus 2w is the matrix 4 minus 8, 2 minus 4 times w equaling v, where it has to be the exact same v from before, is the vector 2, 1. So now I want to solve these equations here. If I row reduce this system, I can divide the first row by 2 and add things together, and I will get that 2 minus 4, 1, 0, 0, 0, which means I need 2w1 minus 4w2 equals 1, and I can pick any values that make that happen. So I can pick, say, 1/2 and 0. So I'm going to pick w to be this vector, and I have v from before. So that means that my second solution should be v t e to the 2t plus w e to the 2t. And then with this, plus our base solution from before, which was just x1 of t is 2, 1 e to the 2t, that will let us get to a general solution for this problem. So that's an example in the idea of what happens for repeated eigenvalues. It gets more complicated, but it ends up being a process where you're multiplying by t and doing the same sort of idea as before to get to the answer. And there is a more formulaic way to write this out that'll come up in the future, but the basic idea and the method is how you want to go about solving these sorts of problems for repeated eigenvalues.